So let's see. This is the lunch offered by Spotify, and we can see there are still lots of people waiting in the queue, and most of them are Swedish. My YouTube viewers, so let's see what is going to happen with this really good company, because they report profit from last year, and they say they have almost 1 million subscribers at this moment. And let's see whether we can have some interesting information from them this year. And now,
backend services. There are many parts of Spotify, clients, web player, content ingestions, and a lot of stuff like that I'm not going to cover. That said, I'm happy to take any questions that you'd like me to ask me, and feel free to interrupt at any time. I'll try to answer them as good as I can. A short background on myself. I've been at Spotify for soon 2 years. I work in our Gothenburg office. We have a smallish, I think we're 25 or so in Gothenburg, tech only. And feel free to contact me if you have any questions afterwards or anything else you're wondering about. ngm@spotify.com, or I'm on Twitter as Protocol7. Yeah.
What's your education background?
That's a very good question, actually, and it's sort of interesting. I'm a biology major. So, I did my PhD studies in Gothenburg on molecular biology, and that sounds weird, I guess, for having this type of work, and well, possibly with your background as well. Turns out that I did, in parallel with my studies, I actually had a company, or 2 different companies, doing consultancy in this area, or the Spotify area, in the web area. It wasn't a huge transfer when I did. And it's actually more of an accident that I switched than something that I had great plans for. Turns out I actually like this, doing the IT stuff rather more than the biology stuff, even though that was fun as well. So that's a major part why I started. So I've been doing this for 13 or 14 years, something like that, full time, and before that on my own with my consultants. Good. Interrupt me with questions. All right, cool. So today, Spotify has somewhere in the neighborhood of 100 backend services. And the service is something that we deploy on a server or multiple servers. I will come back to that. And if you contrast this with many other companies, they tend to build these large, sort of monolithic type of services for many reasons. And companies that I worked with before this, I worked for Volvo and Ford and Sony Ericsson and a bunch of different companies before, and they all tend to build these large monolithic services for many reasons. Spotify has an architecture that is the exact opposite of that. We build very small services. Some of them are just a few thousand lines of code. But we have plenty of them. And that comes with pros and cons, and that's really what this presentation is about. Also, well, I should really have asked, first of all, is there anyone here that is not familiar with what Spotify does and how it works? No? Is there anyone here who's not here for the free lunch? Good. Spotify is fairly large scale. So we have, I think the official number we supposed to release last week is that we have 24 million active users. That's monthly active users. So every 24 million users uses Spotify every month. And that means that we need to handle a fair amount of data and scale to a sort of large scale. Before I started Spotify, I was sort of interested in large-scale systems, but even working for large companies like Volvo and Ericsson, you very seldom work with systems that should support more than, say, a few thousand users. And then coming to a place where you're supposed to handle 20 million users the first day you launch something is a little bit different. And this also has a large effect on architecture. And in the same way, we never want to be down. So we always want to be available. There's a sort of tagline going in the company, which is don't stop the music. And really, at any given point, the user should be able to play music. It might be that we prioritize services, so services which are not really core to the overall experience might have a lower priority on being up, but really the core services should always be up. And this is a gigantic challenge. All right, so this presentation is really on how we choose to build services like this. And the first, well, I should say one more thing. There are really, as you can see, three parts of this. We have many services. They are kind of small. They handle enormous amounts of data, need to scale to really large sizes, and they should always be available. So that's three areas, and I'm going to cover them all in a little bit more detail. And the first is the small service. On the right-hand side is a very, very shallow overview of how we build services, or how our architecture works. So on the top you have the clients. Clients, depending on their abilities, can either connect only to our backend, or they can connect in between each other. We have peer-to-peer in clients, so they can actually, you can fetch music from your peers. But they will always have a connection. Well, unless you're offline, you will always have a connection to our backend. And that connection is to a service that we call the access point. And the access point is a router basically, and it keeps a persistent socket to the client. So as long as the client is connected, it will have a socket to the access point. And the access point will then route and proxy requests coming from clients to our backend services, which is the lower part of the image. Those connections are usually not persistent, but they can be in a few cases. But usually they are common request, stateless request reply APIs. And one of the good things with having these small services that we like to have is when something breaks or when something needs to be scaled down, it's really, really simple to reason about the small and simple code base, and it's increasingly harder the larger that code base gets. The best code base is one that you can actually keep in your mind at the same time and understand the complete process. And we have, as I said, we have services which are very, very small. We have services which are hundreds of lines of code. And then we actually have a few services which are very, very complex. Was there anyone here who saw Jimmy when he was here speaking about our playlist service? All right, cool. So then you know that our playlist service is sort of complex. And it's actually possibly our most complex backend service. The access point might be another one that is also sort of complicated. But most of these are really, really simple. And it really comes down to the Unix philosophy of doing one thing and doing one thing well. And then we compose things out of these simple services. And there's a book called The Art of Unix Programming. Probably something everyone should read. And it has 17 rules of how to build software, and this is, I think this is the first rule, and it's the rule of modularity. And I'm actually going to let you read this because it's not that good. As you might understand, if you don't build very modular, small code bases, you won't get all these benefits. Well, that's the choice you can do, but in our case, we've chosen to go with this. And go read the other 16 of these rules, they're really good. So that means that we need to decouple services. Services should have as small dependencies on each other as possible, and they should, if possible, be autonomous, meaning that whatever happens to another service won't affect this service. And this is really, really good when it comes to making things available. If you couple services, though, so that one service needs to talk to another service, and that possibly needs to talk to the third service, if the third service goes down, you will escape your failure within your package. So we try to make services as autonomous as possible. The first line here is a quote, well, sort of quote from the guy who works at Spotify, and he likes to say this. Decouple until it breaks, and then back off just a little. And that's pretty much how we do things. So we try to decouple things as much as possible, and then we will find that it possibly breaks because of performance reasons or something else, and then we'll possibly, well, moan a little bit and then couple them a little bit more. And we actually work on this all the time. We try to decouple services, even those that are coupled today. So we actually had a case just a few months back where we had this kind of pattern which can be seen in the middle, where the access point would call one of our services called device. That's a service which keeps track of all of these. So per user, it keeps track of the devices that you have and whatever rules there are around them. So for example, you can only offline on 3 devices at any given time, and that's the service which takes care of that. That service made a call to our user service in order to check if the attributes on our user accounts. And most important, checking if you're one of these VIP users who's supposed to be able to offline on more devices. And it turns out that our user service is called by quite a lot of services, and it had a bad reputation of actually being unresponsive. At any given time, another service would just pretty much deny those service to use service, making too many calls to it. And it would get really, really slow, and then this device service would get really, really slow because the user service is slow. And we actually decouple this in a very easy way, that we let the access point keep this VIP status as an attribute on your session when you're connected. And it can decorate the request to the device service with that pretty much a boom. Meaning that all of a sudden the device service is perfectly autonomous and has much better availability. I already said a few things of these. We really like simple code bases, and in order to make code bases simple and smaller, we try to make reuse in libraries rather than in the services. We've had quite a few cases of trying to reuse services. So the playlist service, which Jimmy talked on, is a perfectly good example of that, where the playlist service pretty much stores a list of stuff. And that stuff, or that list should be a playlist, and the stuff should be tracks which are in the playlist. But over time, people have had the need to store other things which are lists, and they've looked at the playlist system and all this thing over here stores lists. Let's use that. And the playlist system has sort of accumulated all types of shit which are lists. And something which seems very much like a list or a playlist when you look at it might over time actually have quite different behaviors. You might have different validation, you might have different scaling patterns, and all types of stuff. Meaning that the playlist system has accumulated all of these weird behaviors depending on, well, I want a list of top users, or I want a list of, well, I want a set of starter tracks, stuff like that. Making the playlist code base extremely complex. Instead, we like to reuse in libraries, meaning that we build separate services that they can share in libraries functionality, but the service itself has a single purpose. The last line is actually in from a different, I used these slides for a different presentation I did on where there was a lot of more enterprisey type of people, and they really like to use patterns and build layers upon layers, and we don't. And you should. When it comes to languages and runtimes, I don't care much about what language you use. In our case, we do use Python and we use Java. When I started Spotify close to 2 years ago, we almost only used Python. Turns out that Python has some scalability, or interesting behaviors under scale, just like that. So some of our heavy-duty systems and core systems, we've switched over to Java, and I think right now we're probably building 50% of the services in Java. And it's not so much Java as a language that we care about, but it's JVM runtime, which is really, really, really good. handles scale very good, has perfectly good imperfections. You can actually look at the runtime system and see how it behaves. Python, well, on the other hand, I think most of you probably program in Java. Right? You get in the courses here. I program in Java since '95, so I've been around for a while when it comes to Java. And it's not my favorite language. I think it sort of generates really ugly code. On the other hand, Python generates really nice code and easily understandable code. Yeah?
How about Python?
That's a very good question, actually. So Python, for those of you who don't know it, is a JVM port of Python. And there are multiple, well, pretty much all these dynamic languages like Ruby or have a JVM port today. The good thing with Python is that it runs on JVM. The bad thing with Python is as soon as you choose to use Python, you no longer have access to pretty much any of the Python libraries around, because they're mostly, or many of them are wrappers around the C extension, meaning that much of the stuff that we use, CRMQ, Cookie Cabinet, currently there are no Python support for those. We could of course build those ourselves, but in this case we picked Java instead. It's a valid question. Yeah.
Why not use any of the other Java even for frontends?
Also very good question. We did actually use Scala, well, I shouldn't say used, we did try Scala for a while. And we did that in a sort of poor way. So instead of doing it in a few services, which was isolated, the guys who did it, which I was one of them, instead did it in our core libraries. And we also did it in sort of poor way. So when then most services still was written in, well, most JVM services was still written in Java. And using Scala APIs from Java sort of sucks. Meaning that Scala got a really bad reputation in Spotify. And it still has. So we've actually actively moved away from Scala. We have not looked into other, I mean, there are a bunch of languages right now in the JVM, like Dojo, Scala, or we have not looked at any of it. Please yell if you have any questions. I might not see you raise your hand. All right, performance and scale. As I said, we get a fair amount of traffic. Depending on what you're used to, it might be humongous amount of traffic or so. For me, it was really large scale when I started working here. And building things for scale and performance is really hard. And there are very few people who are really good at these, and all of them tend to work at Google or Facebook or Twitter. There are certainly other types of performance. I mean, optimizing a particular C code or whatever. But in this case, I'm mostly talking about performance and scale when you have a humongous amount of requests. And the types of services that gets those type of loads are usually these websites like us. Well, we might or might not be a website, but services like Facebook. It's sort of hard to find people who are really good about this. Instead, you really need to care about this. You need to all the time work on improving your performance and your scalability. And the only way it doesn't work for us is we always measure how our services behave. We have tons of graphs and we evaluate them all the time, and we look at them and try to find wherever a service is bounded, I/O, memory, CPU, whatever, and then try to pretty much work off each problem one at a time. And then start measuring it and then keep going. And not all of our services doesn't get all that much requests, but some of our services get a crazy amount of requests. And again, have an architecture that supports this. Again, if you have these large monolithic type of services, it's sort of hard to reason about how they scale. If you get all types of different requests, which has different types of impact on your service, it's really hard to know, well, is it this update for users over here, or is it these get requests for invoices over here, which adds to those. It's really hard to know. In our case, since we only get one type of request to the service, it's much easier to reason. And on that line, we really tend to prefer stateless services. Stateless meaning that, well, they certainly have a state, but we are not mutating that state. For example, some of the services that get most loaded Spotify is those handling metadata. And metadata is, well, let's say you have a track identifier and looking up the track name, the track of the artist name and whatnot for that track is a metadata request. And at any given time when you browse around in any of our clients, you will make multiple requests to one of our metadata systems, meaning that these gets large amount of requests. And the way we scale these are that they are stateless. They have an index, and that index gets updated on currently on a daily basis, and then we can actually patch in changes if we need to. But that index during that day is unchanged, meaning that we can put that into memory. We can make assumptions on caching on that information, for example. We can assume that this information will not update in 24 hours. Let's have the client cache it for a while. And since it's stateless and each of the servers that we have will work independent on any other server that we have for the service, it means that we can scale out this linearly. If we get the double amount of load for one of these services, we just add double amount of servers for it. And we have a fair amount of servers. Our main metadata service is running on 50 or so hardware servers. And in total we have thousands of servers. And when it comes to mutating services, playlist again is a perfect example of this. Users obviously should be able to edit their own playlist, meaning that you need to mutate this data. Again, this makes it much harder. If one of your update requests gets to one of our servers, the playlist has humongous amounts of servers. One of those requests makes it to one server. It is not, and the next request makes it to another server, so the same user. It is not, these servers are not independent of each other. They need to share a state. And as Jimmy described when he was here, we do this for a playlist using Cassandra, which is what's called a column family data store. A very, very good one. But it's a very, very, much more complicated system than having these read-only indexes we keep in memory. So try to isolate these into separate services, because then again you can more easily reason about it. The same way, trying to use efficient protocols. We've been using HTTP protocols for a long time. We had many problems with HTTP protocols, mostly because we sort of suck at using HTTP. And instead we actually defined our own protocol, which is called Hermes. And it's based on top of a messaging infrastructure, which is called CRMQ, which is very, very cool. You should all try it out. And well, one of the problems with HTTP is that when you have HTTP and you have a large amount of servers, again, the access point which I showed you in the picture before, we have, I guess soon we will have about 200 of those servers, and each of those servers run 15 or so instances of the access point, meaning that we have 3,000 instances of access points. And each of these will make requests to services downstream on them. And when they do that using HTTP, for example, it means that we will have 3,000 servers making TCP connections to any given 3,000 instances making TCP connections to any given service, meaning that it will have tens of thousands of TCP connections. And Python, for example, doesn't handle that very good. And then you need connection pools, and they are sort of hard. Again, you run out of them and you need to reason about them. The good thing with using something like CRMQ is that you don't have connection pools, you don't have multiple TCP connections. Instead you multiplex everything over a queue abstraction, which is much it comes to queuing system, I should be clear that there are many types of queuing systems. I've worked for many years on very heavyweight messaging systems like WebServer or stuff like that. That's not what we're using. They would not work under this type of scale. And the same way you want efficient payloads, and you can do this in many ways. You pretty much want them to be small. If they're not small, you will run out of bandwidth on your network spaces. And there are many ways to get small payloads. One way is to just compress it, and that's what you usually do with HTTP, just gzip and send it back. And that works perfectly fine. In our case, we actually use a format called protocol buffers, which Google has implemented. And it uses very efficient binary protocols, or binary payloads. So it's really, really small, even without compression. And you also want fast marshalling, so it's really fast parse and serialize your messages. And protobuf is very, very, very fast. And JSON, for example, is also very fast. XML or other formats might not be as fast. The link is a link to a very, very good presentation that eBay have had a few years back on payloads, where they evaluate exactly these things. How fast are they to marshal and how small are they? And they came up with, I already mentioned Hermes, I'm going to skip this. Oh yeah, we use it for multiple patterns. This is also an improvement over FTP. So the usual way to do things is, Spotify is to do a request reply. So basically, used to the access point, will do a request to a backend service and get a reply back. Very, very common and easy way to do things. We also do publish subscribe. So for example, you might have noticed that if you have two devices where you're playing Spotify and you start, while you're playing it on one device and you start playing on a different device, it will stop playing on the first device. And this is done using publish subscribe. So there's a service called user state, which keeps track of what you're playing at any given time, and when you start playing on the second device, it will actually publish a message to the first device saying that now you need to stop playing. And this is a licensing venue with label. One thing that when I started Spotify, one thing that I have learned over the years going back was that, well, you should do anything you can to not drop requests. Scale out so you're not failing any requests, because any request might be very, very important. And that might be the case. If you have, if you're a bank or a medical company or whatever, you don't want to lose requests. But in our case, many requests that are made are not all that important. A search request that the user makes might not be that important, and it might be perfectly okay to say to the user, this failed, please search again. Instead of trying to build a very complicated solution where every request is fielded. And one problem with trying to deal with every request is when a system gets slow, it will queue up requests that the support is supposed to handle, and queuing up requests usually means that the service gets even slower. And you might get into states where it's not making forward progress. It's getting requests at a higher rate than it can respond to. And that is not a good place to be. And you can try to handle this, and we've done that. I'm going to show you a picture of where we try to do this. But it's usually very, very hard. And usually, if a user makes a search request and we queue that for 2 minutes, it's probably no longer all that interesting to the user. That user has probably searched again or done something else. And when you're in a really bad state, it usually takes hours to get back to the user. Then it's really, really useless. And it's usually a much better thing to say to the user, sorry, I'm going to deal with this request, please try again. So instead of trying to respond to every request that you get, if you're in a bad state, feel free to drop requests and make that aggressively. So we've actually done a lot of work on making our aggressiveness when it comes to dropping requests much more frequent. So, for for example, ways to do this is, since again we're using CRMQ, which is the queuing system, we can use really shallow queues. So instead of storing like hundreds of thousands of messages on a queue, we store 16. Use very short timeouts. Again, the search request might not be that important if it's 10 seconds late, so use a short timeout on that. And use thread pools and connections pools. They're pretty much just a hidden queue. Just if you have a connection pool which can allows for 10,000 connections, that's just a way to queue up another 10,000 requests. So if you want to have small queues, you should also have small thread pools. And this is a picture of one of our systems. This is actually the metadata system I spoke about earlier. And the red area shows the memory usage of this metadata service. And it has exactly the pattern I showed you before on the picture, where it will actually call a search request will come to this metadata service. It will ask the search service for a search, and then decorate that going back to this metadata. And it actually does this for 5 different services. And as I said, the red is the memory usage of this service. And looking at this, you might be able to see when the exact day when I went on vacation. I opened the system, and I went on vacation about July 1st, and I think July 2nd this system just broke down. And it was due to the search service being slow. And that's perfectly fine. The search service can be slow for many reasons. But we need to handle that, of course. But we didn't really. And the reason for this was that this was actually built before I started Spotify, so I don't really know the reasoning behind it. But they were really, really careful about not losing requests. So they made a queue of outstanding requests to the search service, which had 10,000, maximum 10,000 items. And as I said, there was actually 5 of these different services, which means that there was 50,000 items that we could queue. And on each of these servers, which are on the metadata service, there are 15 instances of that service, meaning that we could have 50,000 times 15 outstanding requests, or queued requests. And that's actually the memory usage you can see. That's just queued requests to downstream systems being slow. And the fix that we did, which fixed this, was that we changed this queue to, it's now at a size of 32, which is obviously smaller than 10,000. And as you can see, it's actually been working very good after that. What this picture doesn't show, because it's so scaled up, but you can actually see it if you look really carefully. We had multiple smaller peaks like this before, where we had similar problems. And basically we had this multiple times before we realized that, well, what the problem is. That fixed it. Storage is, again, as I said before, when you have a storage that you need to mutate, you need a very good way to do that. And at Spotify, we sort of like to use safe technologies. We might not be the first adapter of a new technology, especially on new storage. So we use safe ones, and our favorite is Postgres, which is a standard relational database. Postgres does have a problem where it doesn't really scale to large number of writes. So when we have services where we have very many writes, we need to have something else, and then we usually use it. And for these read-only stores, like the metadata services and stuff like that, we use multiple different ones. Token Cabinet is a favorite. We have our own, we use Lucene or a few others. And the link is to a very good blog post of a colleague of mine who wrote on basically our use of Postgres and Cassandra. And we always want to be up. We always want to be available. It should always be possible to play music. And when you have a few thousand servers like we do, at any given time, many of them are broken. And you can't build your way around that. Stuff will be broken. Instead, you need to deal with stuff being broken and work based on that assumption. So, for example, we always deploy services to multiple servers. So when you design your service, you need to make it handle that there will be multiple instances of it running at any given time. In our team, for example, we never deploy a service to less than 9 physical hardware servers. We have 3 data centers at the moment, and we never deploy to less than 3 servers per data center. And you always need to monitor your things, so otherwise you don't know if it's broken, and then you're really in the bad state. You have very good monitoring and good alerting systems, so you will actually get an SMS or an email or whatever when something breaks. And don't deny of service yourself. This is a specialty of us. We do this all the time. So when you have millions of clients running, even a very small problem in those clients where it, for example, will make, if something fails, it will make retries for something over and over again at the same rate. That's a very good way of denial servicing yourselves. And we did this, the last time we did this was Friday, I think. I can actually give that example. We have a service called Pop Count, and it keeps tracks of how many subscribers there are to a playlist. Very, very simple service. And the client will ask, when it shows the playlist, it will ask the Pop Count service for how many subscribers are to this playlist. And it will basically reply back with an integer saying 13. Not that far. It went down for multiple reasons, and the client doesn't have a backup, so it will keep asking the service for this subscriber number every second, and it will do this from many clients, meaning that when this went down, it went down because of completely different reasons. You can't actually get it up again, because as soon as you get an instance up, you will get millions and millions of requests per second, and it can't handle that. We have multiple instances of this up and running, but getting the first one up, and it will get all the requests, and it will die again. So we actually have to firewall and do tricks like that in order to get stuff up and running again. And we need to fix the client, obviously, but and we do this all the time. There are so many ways, if you have a large number of clients, to do this to yourself. It's it's stupid, but it's not good. I mentioned this. I sort of mentioned this. We as I said, we deploy on many servers. We don't like to buy humongous servers which cost millions of money from IBM or somewhere. We buy commodity servers from Dell, I think. The normal off-the-shelf servers that pretty much any company would use, but we use many of them. Since we have many of them, you need to have a good way to find a particular service within these hundreds of servers. And for this, there are many ways of doing this, many fancy ways, and we use a very simple way, and we just use DNS. And there are a particular type of DNS record called the SRV record, which is very clever because you can actually ask DNS for a service rather than, DNS is used for a records where you put in Google.com and you get an IP address back. SRV records instead, you ask for more of a logical things. You ask for, I want the playlist service in London, which is one of our data centers. And it will return back to you, well, the playlist service in London lives on these servers and on these ports. And there are actually weights and priorities, so you can say, well, this server, which is larger than the other ones, should get more load and stuff. Very, very clever, very awesome with that. And when you have hundreds of servers, you need to have deployment and configuration automated and repeatable. Humans are great, but they're not great for doing repeating stuff because we find it boring and we make errors. So instead, you really need to have a way to automate this, and I'm going to come back and do it. I think, and as I've said multiple times, you need to measure everything and be really careful in actually measuring any behavior that could break your service. And for Python, we have our own metrics library, and for Java, we use one developed by Coda-A, which is a, well, he was the developer at Jammer, which was bought by Microsoft, so now it's and you don't only need to monitor your service, you always need to monitor your infrastructure as well. So your operating system, your memory, whatever. The graph I showed before was memory usage. You need to measure that as well. And obviously you need to graph it. So that graph I showed was a screenshot from our sort of poorly working monitoring system, but it's being worked on all the time. It turns out that building a monitoring system when you have thousands of servers with many metrics on each server is kind of hard. And we use a system called Union, which is an open source system, which we've been building on, and sort of it's a largely changed service. And in the same way as you should measure your stuff, you should also log whatever is important. And you should use a structured format. So when I came to Spotify, I was used to logging everything, but I wasn't used to using a structured format. So we would just write out whatever was important. And well, that's better than nothing, but it's really hard to actually use your logs afterwards to make analysis on your server. So instead, we use the structured format, basically just a tab-separated format, and then we have a way of parsing those and actually knowing what every digit means and having a versioning for it, so we can add in more stuff without breaking the old stuff. And then we collect these logs into a central place. And there are many ways of doing this. In our case, we have a very simple way of just r-syncing files over to our Hadoop file system, which is a humongous file system with tons of data. And we save logs for a significant amount of time on this file system. What's important when it comes to storing logs is that you should have a privacy policy towards your users, and you cannot store logs which fails to comply with that privacy policy. So that's important when you store logs. And then we analyze logs quite a lot, and just don't know who's doing this all the time right now. We run a lot of analysis on our logs, both to know how users behave and also to know how systems behave. It's very, very useful. I said before you should automate deployment. We run everything on Debian Linux servers, Debian Squeeze at the moment, and we build everything into Debian packages. When you deploy something, you should use Linux, and you should use whatever packaging system your Linux distribution uses. So if you use Debian, you should use Dev packages. If you use Fedora or Red Hat, you should use RPM packages or whatever. Make use of them. They are fucking awesome. They do everything for you. They thought of everything when it comes to dependencies and conflicts and whatnot. It's extremely good. I've built sort of similar looking systems before realizing that these did everything for us. And it's really hard actually for many reasons. But again, they have chosen to do this and it's useful. The only exception that we have is for Java dependencies where we use Maven instead of Debian. But for everything else we build